Hey everyone, Akil from Oxen Academy here. Today we are going to be defining the derivative, or finding a mathematical definition of the derivative. So let's go ahead and get started. So let's say we had this function right here, f of x, and we're going to let this equal y. This is our x-axis and this is our y-axis. If we go ahead and we take 2 points, all right? So this is our point right here, x1, y1. This right here is x1, and this is obviously y1, all right? And then let's go ahead and take another point right here. This is x2, y2. All right, so we got x2 and y2, all right? So let's go ahead and draw the line that connects both of these points. So this line right here is what we call a secant line. And this secant line right here has a slope, for as you remember, of y2 minus y1 over x2 minus x1. Remember this from Algebra 1. And this right here is what we call the average rate of change. But what if we could apply this average rate of change to 1 point? Well, it wouldn't be average anymore, but it would still hold the same idea of it being a rate of change. So how are we going to do that? What if we brought these quantities x1 and x2 together to be so extremely close that we effectively had just 1 point? And we'll call this point right here xy. So what I'm going to do is I'm going to draw the line that intersects this graph at exactly 1 point and at this 1 point only. So this line right here is what we call the tangent line, or the line tangent to the graph. And this slope right here, m tangent, we don't really know what it is. Well, we can go ahead and zoom in on this graph. Let's say this is about a 10,000 window zoom. And what we can do is we can go ahead and draw this line right here. And if you notice, this right here, this is pretty much just 1 point. All of this right here is just in 1 point, okay? So this distance right here, we're going to call this distance actually dy, and we're going to call this distance dx. And we use d instead of delta. Well, we didn't really use delta here, but if you want, you can go ahead and write it right here, delta y over delta x. It's the same idea. But we use d here because it's a really small rate of change, or really small change, or what we call an infinitesimally small change. So this slope right here, m, this slope is equal to m tangent. This is equal to dy over dx. And this is one way to notate derivatives. And the way we get this dy dx form, notice we zoomed in 10,000, but in reality, we really just brought x1 and x2 closer. So we know that this distance is delta x, but by bringing these closer, we're limiting delta x to 0. This is the limit as delta x goes to 0 of delta y over delta x, because that is our slope formula. So delta y over delta x. And how do we go ahead and put this into function notation? Because we know y equals f of x. Well, this is actually the limit as delta x goes to 0 of f of x2 minus f of x1 over delta x. But what is x2? x2 is actually, if delta x is x2 minus x1, x2 is equal to x1 plus delta x. And so therefore, we get that this is equal to the limit as delta x goes to 0 of f of x1 plus delta x minus f of x1 over delta x. And this right here gives us our official definition of a derivative. The real formula that everyone is given, the limit as h goes to 0, h is just our variable for change, f of x plus h minus f of x over h. And this formula right here is our mathematical definition of a derivative. So that concludes this video on defining a derivative. This is Akil from Oxford Academy signing off, and I hope to see you in future videos.